Hey everyone, welcome to This Explainer. Today, we're going to crack open the ultimate black box, how software actually runs. You know, when we sit down and write a brilliant script, it feels almost like magic when the computer perfectly executes our commands. But it isn't magic at all. It's a meticulous, incredibly high-speed journey of translation. Okay, let's just dive right into this. At the very center of all software engineering, there's this one fundamental mystery, right? How does human-readable text, the words and symbols we actually type on our keyboards, become physical, electrical action inside a microchip? The answer lies in the layers of translation that happen in the absolute blink of an eye. Here's our roadmap for today. We'll start with machine code versus bytecode, then unravel the famous Python paradox. After that, we're looking at source-to-source translation, and finally, the limitations of those S-to-S compilers. All right, section 1, machine code versus bytecode. To really grasp this stuff, we have to start at the absolute lowest level. So the end of the line for any program is machine code. This is literally the lowest level representation of your source code. It's the final platform-dependent language that your CPU actually reads, pure binary, zeros and ones. At this point, the CPU doesn't need any more translations. It just reads the binary and physically executes the actions. But, and here's the catch, because it is custom-tailored to specific hardware, machine code generated for one platform absolutely will not run on a completely different operating system. And that exact hardware limitation brings us to bytecode. Now, bytecode is this brilliant intermediate step. Unlike machine code, your computer's hardware cannot understand bytecode directly. It's a non-runnable middleman. But the beauty of it is that it's totally platform independent, super portable. The trade-off is that it requires a virtual machine, like the Java virtual machine, for example, to translate it into machine code on the fly for whatever system it happens to be running on at the time. When we put them side by side, you can really see the contrast here. Machine code gives you that blazing fast, direct CPU access, but you're permanently locked into that specific hardware architecture. Bytecode sacrifices that direct access. It relies on a virtual machine to do the heavy lifting, but in exchange, you get universal portability. You can literally take that bytecode and run it anywhere the virtual machine is installed. Section 2, the Python paradox. Now that we've got those basics down, let's look at a real-world example that constantly trips up even veteran developers. Let's talk about Python. For almost 15 years now, there's been this massive debate raging on Stack Overflow, hundreds of thousands of views, dozens of super detailed answers, all fiercely arguing over one seemingly simple question. Is Python interpreted, compiled, or both? To really get why people are so confused, check out this quote from the original poster on Stack Overflow, Pankaj Upadhyay. He wrote, "Everywhere you learn that Python is an interpreted language, but it's interpreted to some intermediate code and not to the machine code." He hit the nail right on the head. If Python is just an interpreted language, why in the world is it generating this intermediate bytecode, and what is actually running it? Well, the crucial point is revealed by the broader community. Python actually compiles your code behind the scenes before interpreting it. You know, we casually call Python an interpreted language, but that's technically a property of the implementation, not the language itself. The standard implementation, CPython, actually does both. It silently compiles your human-readable script into bytecode first, purely to speed up execution. Let's break down the actual pipeline so you can see exactly how a Python script runs. First, you've got your source code, your .py file. When you hit run, the Python compiler parses it and translates it into bytecode. That's often saved as a .pyc file. That bytecode is a low-level, platform-independent representation. Finally, that bytecode is shipped off to the Python virtual machine, or PVM. The PVM is basically this massive loop that just iterates through your bytecode instructions one by one, translating them into actual machine execution. So, long story short, Python is compiled to bytecode, and then that bytecode is interpreted by the virtual machine. Section 3, source-to-source translation. Okay, so we've seen how standard compilation works. Let's shift gears and look at a much higher-level tool used by high-performance computing researchers. We're moving from translating code into machine instructions to translating code into, well, more code. Enter the source-to-source, or S2S, compiler. You might also hear it called a transpiler. This is a tool that takes source code in and spits equivalent source code out, either in the same language or totally different high-level language. And all of this happens before a traditional compiler ever gets involved. In the world of high-performance computing, this sounds incredible. It's used for massive refactoring jobs, injecting analysis tools, or porting giant scientific applications to new parallel platforms. But, as researchers are quickly finding out, it comes with some pretty serious baggage. And this brilliantly illustrates the reality of actually using S2S. Researchers from OSTI did this incredibly rigorous literature review. They started with a massive query of over 1,700 papers related to S2S compilers. But after carefully filtering and categorizing, they narrowed it all down to a core group of just 29 relevant studies that specifically explained why high-performance computing practitioners actually avoided using S2S tools in their own workflows. Which brings us to Section 4, Limitations of S2S compilers. This is where the narrative really twists. S2S compilation is almost always pitched as this magic bullet for code portability. But the study identified 5 major reasons why top practitioners are extremely hesitant to use them. First, S2S transforms can actually interfere with optimizations downstream. Second, they're surprisingly hard to extend to new programming models. Third, using a transpiler creates complex, fragile workflows. Fourth, parsing complex source code is just inherently difficult to do right. And fifth, S2S is often just a temporary stopgap for missing features elsewhere. Let's unpack that first and fourth point because they absolutely go hand in hand. Parsing a complex language like C++ is absurdly difficult. When an S2S tool modifies your source code, let's say to add performance tracking, it's acting kind of blindly. It might inject code that inadvertently blocks your downstream compiler from doing its job, like performing crucial memory or floating point optimizations. So paradoxically, the tool you're using to improve performance can end up actively destroying it by completely blinding the downstream compiler. The researchers, McCormick and his colleagues, summed it up perfectly. They wrote, "The loss of domain-specific knowledge is inherent in source-to-source compilation techniques that, by design, split the toolchain into disjoint infrastructures. Essentially, by jamming a middleman transpiler in there, you fracture your toolchain. The high-level intent you had as a developer gets totally lost in translation before it ever even reaches the final compiler." And that leads us to the final and maybe most impactful limitation. S2S is often just a temporary band-aid. The review found multiple cases where developers spent huge amounts of time building complex S2S tools only to completely abandon them the second hardware or native libraries evolved. For instance, developers used S2S to map OpenCL code to FPGA hardware. But as soon as Xilinx Vivado HLS added native support, the S2S tool was totally obsolete. Same thing happened with GPUs. Complex data placement transpilers were instantly abandoned once NVIDIA introduced unified virtual addressing and NVLink. The hardware simply caught up and fixed the problem itself. From Python relying on this hidden bytecode translation to massive supercomputers struggling with fragmented transpilers, the way we translate human ideas into machine action is constantly shifting. And it leaves us with a pretty provocative question. As native compilers get smarter and hardware architectures become endlessly more adaptable, will we eventually see a day where these intermediate steps, all these middleman languages, are rendered completely obsolete? Thanks for joining me for this explainer, and keep questioning the code behind the curtain.